Today we're talking about right triangles, squares, Pythagorean theorem, how it works. The general idea behind it is if I were to take a set of squares, let's say a 3 by 3 and a let's call this a 4 by 4 square here. I don't know if it's exactly to scale, but let's just say it's close enough. This measurement from these 2 points, in which we see we've just created a right triangle, would be the side of a square, which would have the total amount of squares, for instance, this being 9 and this being 16, would have the total amount of squares, 9 plus 16, 15. And we could kind of identify that this side was 5. It's the idea that if we take the two squares that make up the sides of the triangle, add up their total amount of squares, mind you, each of these squares is like a 3 by 3. We're looking at the 1, 2, so on and so forth, the 9 squares. If we add those up, we would create a square which would have a total amount of 25. Let's fix that. 25 squares, and the side of that square would in fact be this side of your triangle here, in which we essentially call a hypotenuse. So in a right triangle, you have this relationship of two legs and a hypotenuse, and the square of those two legs, or the sum, if we add those up, right, 9 plus 16 is equal to 25. So the square of those legs, a leg squared, plus a leg squared is equal to a hypotenuse squared. We'll just call it a hypotenuse for short, squared. And what you'll see a lot of is, well, if I want to know what this hypotenuse is, then essentially I'm just going to take the square root of each side here, and essentially my hypotenuse is the square root of my leg squared. This is this Pythagorean theorem, this understanding here that we're working with, how a hypotenuse is the square. So if I take 9 plus 16 and take the square root of that, square root of 25, 5, that is this side here that we're working with. This is this understanding that we're trying to come to. Now we can use this idea, triangle, as long as they provide us with a right angle, and we can use this to solve for any missing side of the triangle. First, we want to identify which piece we're solving for. So we'll start with hypotenuse. We'll solve for hypotenuse here. We'll just call it h. We're solving for the hypotenuse. And we know that our x is equal to our sum of our 8 squared plus 6 squared. Now what you'll see a lot is this idea of, they call the legs the a and the b and the hypotenuse the c, and they'll say a squared plus b squared is equal to c squared, or they'll write it as c squared is equal to a squared plus b squared. And if we're working with that, that is where we get our c squared is equal to 8 squared plus, we'll do it 2 different ways here, plus 6 squared, which is equal to 64 plus 36, which is equal to 100. C squared is equal to 100. Take the square root of each side. C is equal to 10. So here we have, okay, this is our side of 10. Same if we put this into our calculator, we get x equals 10. Just kind of this idea of solving for hypotenuse. Now you could use this same theorem. And let's say we're going to, it's a terrible S there, we're going to solve for an L, or a leg, or an A or B. we use the A or B as the legs here. And we have, again, we'll start with a right triangle. Let me do a 9 and 15. We'll do, now identify that the side opposite the right angle here, that's always going to be our hypotenuse. Okay, so when we're solving for a leg, there's going to be a little bit of subtraction involved there. We're going to look for some subtraction here. And I'll try to look at it in a couple different ways, but we could just kind of say, okay, this is my A, this is my B, and here's my hypotenuse. We could call this the leg squared plus the leg squared. But let's just say A squared plus B squared is equal to C squared. You're going to hear that over and over. And let's say our A was 9, so we have 9 squared plus B squared. We don't know the leg, and that's equal to our hypotenuse, 15 squared. So I have 81 plus B squared is equal to 225. Subtract 81. And I get B squared is equal to 144. Take the square root. B is equal to 12. And this is how we're solving for our leg here. Now you may see this idea that some will solve for the B first. So for instance, they'll do minus A squared, like if I'm solving for the B, minus A squared. B squared is equal to C squared minus A squared. Take the square root of each side. B, or your leg, is equal to the square root of C squared minus A squared. This is like the simplified form in which we want to maybe more quickly plug in and solve. Leg squared minus hypotenuse squared. Oh, I apologize. That should be the hypotenuse minus the leg squared. Just this idea of, what are we doing when they give it to us? Maybe this is kind of the quicker way we could plug in our values. And what I've kind of secretly done, as I've done this, just a Pythagorean triples, where you have whole numbers, 3, 4, 5, 6, 8, 10, 12, I'm sorry, 9, 12, 15. You have this 5, 12, 13 is a funny one, where the whole numbers squared will equal to a whole number hypotenuse squared. So, that 9 plus 16 equal to 25. That you have these perfect, maybe you could call them perfect right triangles, where the legs squared, whole numbers are whole numbers, and they equal a hypotenuse, which is a whole number. And the reason I'm bringing that up is because a situation where you have two sides of a triangle. Actually, let's just look at an isosceles triangle here and here, and we'll give it sides 4 and 4, and we're asking for a leg. This is a little bit different here because when we set it up, 4 squared plus 4 squared are 2 legs equal to hypotenuse squared. We don't end up with a perfect square. Let's call this remaining. Now, perfect square of 16 is 4. Square root of 20, well, there isn't any number times itself that equals 20. So what we need to do is actually simplify the radical, and you end up with 2 square root of 5. So there's this idea of a perfect square versus a non-perfect square. So in some of your solving of missing sides using the right triangle, you will end up with, for instance here, a 32. And you will take a square root and you'll say, well, x equals square root of 32, and it'll ask for a simplification. Now, you could just put this as a decimal, and this is somewhere in between 5 and 6, so it would be 5 point a number, or they'll ask you to simplify that radical, and you'll have to say, well, I know 8 times 4 is 32, and I know I could break down this 8 into 4 and 2, and I have a repeat of a perfect square radical 4, so my answer would actually end up being x is equal to 4 square root of 2. And if you don't understand that repeat, square root of 4 times square root of 4 is square root of 16, and square root of 16 is 4. That's where that comes from. And this would be your answer here if they were asking for simplify in radical form. So just a good basic intro of where the Pythagorean comes from, how to solve for hypotenuse in a leg, Pythagorean triples, where you have whole numbers equal other whole numbers, where you don't have decimals or radicals. And here's one where we're solving for hypotenuse, where we have a radical which cannot be simplified into a whole number integer. It's not a perfect radical, and either we need to give a decimal answer or simplify in radical form. The more you fail, the more you succeed. That's why we continue to work hard and practice. So thanks for stopping by.